Okay, space fans, get ready for a little cosmic curveball. Because we're diving deep into the world of gravitational waves today, but with a twist you might not see coming.
I'm intrigued.
White dwarfs. These fascinating stellar remnants. They kind of get overshadowed by their more dramatic cousins, black holes.
Yeah, it's true. Black holes tend to kind of hog the spotlight when we're talking gravitational waves. But you know, what I find so interesting about this deep dive is that it shines a light on the unexpected power of white dwarfs. They might be small, but they've got a gravitational wave secret that's about to change the game.
Exactly. And this secret has huge implications for an upcoming mission. It's called LISA, the Laser Interferometer Space Antenna, set to launch in the mid-2030s. LISA is going to be humanity's giant ear, tuned in to the symphony of gravitational waves from all corners of the cosmos, including black holes of all sizes. But, as we're about to find out, the soundtrack might be dominated by something entirely unexpected. A chorus of white dwarfs.
Imagine you're trying to eavesdrop on a conversation at a really bustling party. You know, you're straining to hear the whispers of a few individuals. But then you realize there's a whole other conversation happening, a constant hum from a much larger group that you initially just overlooked. That's kind of what's happening with LISA and white dwarfs.
Okay, I'm intrigued. How did we uncover this hidden conversation?
Well, two master's students from Radboud University, Seppa Stylens and Sophie Hoffman, they were working with astronomer Gisha Snellemans, and they decided to investigate something that most astronomers thought was impossible. They wanted to see if LISA would be sensitive enough to detect the combined gravitational wave noise from white dwarfs.
What did they find?
Their models revealed something groundbreaking. You know, because white dwarfs are so incredibly numerous and they have such long lifespans, their combined gravitational wave signal, even if individually faint, could actually drown out the signals from less common but individually more powerful sources like black holes. As Stalins put it, and I love this quote, and now our models show that the white dwarfs are dwarfing the black holes.
The white dwarfs are dwarfing the black holes.
I
love it. It's amazing how a simple statement can encapsulate such a profound shift in our understanding. But before we dive deeper into why this is such a big deal, let's make sure everyone listening is on the same page about what makes a white dwarf so unique.
Yeah, you're probably familiar with the basic idea of a white dwarf. It's essentially the leftover core of a star, like our sun after it's exhausted all its nuclear fuel. But what makes them so intriguing, especially in the context of gravitational waves, is their mind-boggling density. So picture this. The entire mass of the sun compressed into something the size of Earth.
Whoa, that's denser than anything I can imagine.
Yeah.
I'm starting to see why we might have underestimated their gravitational influence.
Exactly. That kind of density generates some pretty intense gravitational forces. And while a single white dwarf's gravitational wave signal might be faint, when you consider that there are billions upon billions of them scattered throughout the universe.
It's like suddenly realizing that the quiet hum of a million bees can be louder than the roar of a lion.
Yes, exactly.
It completely changes your perception of the soundscape.
Precisely. And that's what these students have done for our understanding of the gravitational wave universe. They've revealed a hidden layer of sound that we weren't even aware of before.
Okay. I have to admit, when I first read about this, I was floored. It makes you wonder what other secrets the universe is hiding in plain sight. But I'm curious, how does this change our understanding of white dwarfs themselves? They're no longer just these quiet, fading embers of dead stars, are they?
Not at all. This discovery tells us that white dwarfs are far more dynamic and influential than we previously thought. It opens up a whole new avenue for studying their evolution, their composition,
and their role in the larger cosmic ecosystem.
So what's next? How do we go from this groundbreaking discovery to actually unlocking the secrets of white dwarf gravitational waves?
Well, for starters, the research published by Stalins and Hoffman in not one, but two separate papers in astronomy and astrophysics is just the beginning. We need more detailed observations, better models, and sophisticated data analysis techniques to really harness the potential of this discovery. But with LISA on the horizon and the ingenuity of scientists around the world, I think we're on the verge of an incredible new chapter in our exploration of the universe.
That's an excellent point. This isn't just a one-off discovery. It's a launch pad for a whole new era of research. But before we get too far ahead of ourselves, let's delve a little deeper into the specifics of white dwarfs and why their gravitational waves are so valuable. This discovery has implications far beyond just LISA. It connects to some pretty fundamental questions about the evolution of stars, even the fate of our own sun. You're right, this goes far beyond just abstract astrophysics. It touches on some very profound questions about the universe and our place within it. But to really appreciate that connection, we need to take a closer look at what these gravitational waves can actually tell us.
And that's exactly what we'll be doing in part 2 of this deep dive. So stay tuned, listeners, because things are about to get even more fascinating.
So we've established that white dwarfs are far more significant in the gravitational wave arena than we initially thought. But why should we care? What can their gravitational whispers actually tell us?
Yeah, that's the question I was hoping you'd ask. I mean, it's all very fascinating.
Right.
But how does it relate to us here on Earth?
Well, think about it this way. For centuries, astronomers have relied on light to study the universe.
Okay.
Telescopes are essentially giant eyes capturing photons from distant stars and galaxies.
Right.
But light can be distorted, absorbed, or even completely blocked by interstellar dust and gas.
Right, so it's like trying to listen to a conversation through a thick wall. You might catch snippets, but you're missing a lot of the detail.
Exactly. But gravitational waves are different. They're like ripples in the very fabric of space-time, and they travel unimpeded across vast cosmic distances. They carry information about the objects that created them, like fingerprints at a crime scene.
Okay, I'm starting to see where you're going with this.
Yeah.
So, by listening to the gravitational waves from white dwarfs, we can learn things about them that we could never glean from light alone.
Precisely. We can learn about their mass, their rotation, their composition, even how they interact with their surroundings. And here's where it gets really interesting. Remember, white dwarfs are the end stage of stars like our sun.
You're not going to tell me that by studying white dwarf gravitational waves, we can actually peek into the future of our own solar system, are you?
Well, in a way, yes. By studying white dwarfs in other parts of the galaxy, we're essentially looking at a snapshot of what our sun will become billions of years from now. We can compare their properties, their evolution, and use that information to refine our models of stellar evolution.
Wow, that's pretty mind-boggling. It's like having a time machine, but instead of traveling through time, we're listening to echoes from the future. It's making me feel both incredibly small and strangely connected to the grand scheme of things.
I completely understand that feeling. It's humbling to realize that these tiny, seemingly insignificant white dwarfs hold clues to some of the biggest questions about the universe, including the ultimate fate of our own star.
Okay, so we've established that white dwarf gravitational waves can provide valuable insights into stellar evolution. But what about the bigger picture? What about the potential to uncover hidden chapters in the story of the universe itself?
Ah, yes, the whispers of the early universe. Remember we talked about the background noise of gravitational waves?
Right.
Well, if we can filter out the dominant signals from black holes and white dwarfs, we might be able to detect even fainter signals buried beneath that noise.
Like what, signals from the first stars?
Yeah.
Or even from the Big Bang itself?
Exactly. It's a long shot, but it's not entirely out of the realm of possibility. The early universe was a chaotic and energetic place, and those events would have left their mark on the fabric of space-time.
So it's like trying to hear a whisper in a hurricane.
A very accurate analogy. But with LISA's incredible sensitivity and the advanced data analysis techniques being developed, we might just be able to tease out those faint whispers and learn things about the early universe that we could never have imagined before.
This is blowing my mind. So we've gone from being surprised by the strength of white dwarf gravitational waves to realizing they could be the key to unlocking some of the universe's deepest secrets. It makes you wonder what other surprises are lurking out there waiting to be discovered.
That's the beauty of science, isn't it? It's a never-ending journey of discovery, and every answer we find often leads to even more questions. But to really appreciate the potential of this discovery,
we need to understand how scientists are planning to translate these faint whispers into tangible knowledge. Okay, so what are the next steps? What's the roadmap for turning these theoretical possibilities into concrete scientific discoveries?
Well, the models developed by Stalins and Hoffman are a fantastic starting point,
Okay.
but they're still based on certain assumptions about white dwarf populations and their evolution. The next step is to refine these models with more detailed data from current telescopes.
So it's like we've built the telescope, but now we need to calibrate the lenses to get a clearer picture.
Precisely. We need more precise measurements of white dwarf masses, their temperatures, and their orbital periods if they're part of a binary system.
Right.
This will give us a better understanding of how these factors influence the strength and frequency of their gravitational wave emissions.
I imagine there's a lot of collaboration happening between the teams working on LISA and those studying white dwarfs with traditional telescopes. It sounds like a truly interdisciplinary effort.
Absolutely. It's a testament to the collaborative nature of modern science. Astronomers, physicists, computer scientists, engineers, they're all working together to prepare for the deluge of data that LISA will bring.
Okay, I'm sensing a theme here. It's all about preparation, refinement, and collaboration. It's like we're gearing up for a grand symphony, making sure all the instruments are tuned and the musicians are in sync.
A very apt analogy, and it's not just about gathering the data. It's about developing the tools to analyze it.
Right.
Think about it. We're talking about trying to isolate incredibly faint signals from a sea of gravitational wave noise. It's a computational challenge of epic proportions.
So it's like trying to hear a pin drop in the middle of a rock concert.
You could say that. But thankfully, researchers are developing incredibly sophisticated algorithms and machine learning techniques to sift through the data and extract the whispers of white dwarfs from the cosmic cacophony.
This is all incredibly exciting. It sounds like we're on the cusp of a new era in astronomy where gravitational waves become just as important as light in our quest to understand the universe.
Indeed. And who knows what other surprises await us as we delve deeper into this new realm of cosmic exploration. Perhaps we'll find that the most unassuming objects, like white dwarfs, hold the keys to unlocking the universe's greatest mysteries.
This is why I love these deep dives. It's like taking a journey into the unknown, guided by experts who can illuminate the path. And on that note, I'm eager to hear what's next on our roadmap of discovery. What other challenges and opportunities lie ahead in this quest to unravel the secrets of white dwarf gravitational waves?
Well, that's a great question, and it leads us to the cutting edge of what scientists are working on right now. You see, while these advances in data analysis are crucial, there's another challenge that we haven't talked about yet.
So we've been talking about the incredible potential of white dwarf gravitational waves to reveal secrets about stellar evolution and even the early universe. But before we wrap up, you mentioned another challenge.
Facing scientists in this field?
Right.
What is it?
Well, we've talked about refining models, developing powerful data analysis techniques. But there's another crucial element that's often overlooked: theoretical understanding.
Okay.
You see, while we have a good grasp of the basic physics behind gravitational waves when it comes to white dwarfs, there are still some gaps in our knowledge.
Okay, let's unpack that. What kind of theoretical gaps are we talking about?
For example, we need to better understand the internal structure of white dwarfs, particularly how matter behaves under such extreme densities.
Right.
We also need to refine our models of how white dwarfs form, evolve, and interact with their environments, especially if they're part of binary systems.
So it's like we have the blueprint for the building, but we're still figuring out the best materials and construction techniques.
That's a great analogy. We need a deeper theoretical foundation to make sure we're interpreting the gravitational wave signals correctly. For instance, the specific frequencies and patterns of these waves can tell us about the processes happening inside the white dwarf.
Okay.
But we need robust theoretical models to decode those signals accurately.
That makes sense. It's like learning a new language. You can hear the sounds, but without understanding the grammar and vocabulary, you can't fully grasp the meaning.
Exactly. And that's where theoretical astrophysicists come in. They're working on developing sophisticated simulations and calculations to better understand the complex physics governing white dwarfs and their gravitational wave emissions.
So it's a two-pronged approach then. Refining our observational capabilities with LISA.
Yes.
While simultaneously deepening our theoretical understanding.
Precisely. It's a beautiful interplay between theory and observation.
Right.
Each informing and pushing the boundaries of the other. And it's the synergy that will ultimately unlock the full potential of white dwarf gravitational waves.
This has been an incredible journey. We've gone from being surprised by the strength of white dwarf gravitational waves to realizing they hold clues to the evolution of stars, the secrets of the early universe, and even the future of our own solar system.
It's amazing.
It's a testament to the power of scientific curiosity and the importance of exploring the unknown.
It is truly remarkable, isn't it, how something as seemingly faint as the gravitational whisper of a white dwarf can resonate with such profound implications for our understanding of the universe.
As we conclude this deep dive, I'm left with a sense of awe and excitement for the future of astronomy. Who knows what other wonders await us as we continue to listen to the symphony of the cosmos?
Indeed. And perhaps as you gaze up at the night sky, you'll see those twinkling stars not just as points of light, but as potential sources of gravitational waves, each with a story to tell about the grand narrative of the universe.